Okay, I have one more data set to play with. Let's look at that. This is river gauge data. So this is time every 15 minutes. So these are minutes, and it's for a few days. So there's a lot of minutes here. And we have the height of the gauge. And this was after a rain event. So this is the Little Tennessee River. It's a river I've paddled many, many times down in North Carolina. You would expect it to be in Tennessee, but, well, at this point it's in North Carolina. It's Little Tennessee River. It's down south of the Smokies. So if you were to go through the Smoky Mountains into North Carolina, you would be near the Little Tennessee River. And so this is a lot of data. And you know, you thought maybe the 365 was big. Well, this is really big. I think this is maybe 700 lines or 800 lines or something like that. So I'm highlighting all of it. Yeah, 730 lines of data. Okay, and I copy. I go back here, and again, I click in there and I do a Control V to paste my data, and there it is, and it got all the rows, and wow, you know, that's a lot. Okay, now move my lovely picture. So as we're looking at the data, you know, what I see is something that's kind of coming down like this. Here is the y-intercept. If you look at these tiny numbers down here, that's 5,000. This is 10,000. So, you know, this is really a very compressed scale, and we're up here at 2.4. So as I look at this, to me, given that it looks like, you know, it will probably want to head to a horizontal asymptote, and yes, indeed, it should have a value here on the y-axis, have some sort of y-intercept. Then I would say I'm going to try an exponential model. So I have f of x is equal to e to the x. Okay, wow, you know, look at that. There's e to the x, and it looks like it's just the y-axis. So we've got a lot of work to do. So g of x, again, is equal to a times f of b, x minus c, like that, plus d. And I will add all those, and it's a blue line. I think I'm gonna go up here. I'm gonna change that to orange, too close to purple, and there we have these. Now again, similar to the x squared or the quadratic, when I look at e to the x, now if I have e to the x plus something up here in the exponent, you know, a plus c of some kind, or minus, doesn't really matter, but think about it as a plus c. Well, that's actually e to the x times e to the c. Okay, but that's what a is doing. You know, e to the c is a constant. That's what a is doing. So really, we don't need to mess with c here, or we don't need to mess with a. But as I know that a is going to give me my y-intercept here with a d of 0 anyway, but the a has to do with the y-intercept. That's going to be easier for me to work with than this this c, because of the, you know, fact that the actual multiplication you're getting, you would have e to the minus bc as your multiplication. You know, so moving it side to side, which c does, is going to do the same thing as a, which is kind of move it up and down as far as a y-intercept. But it really isn't going to do anything different than that. So c, I want that to be 0. Okay, I don't want c to have anything to do with this. So we'll just leave c alone. We'll mess with a and b. Now, quickly, I can see that D, which is how much I need to raise it up for a horizontal asymptote, because usually e to the x, if it's decreasing like this, it has a horizontal asymptote at 0, and so this is like 2, there's 2.4, 2.6, 2.5, 2.55. Yeah, I'm going to try a horizontal asymptote of 2.55. Okay, so I'm going to do that. And now notice it's over here. Well, that's because my b, my multiplier on the exponent, is still a positive number. And so this 2.55, well, I want to make it easier, so I'm going to go between 2.5 and maybe 3, something like that, so that when I start doing small changes, it's much easier to do. A, on the other hand, well, okay, if I'm already at 2.55, then A, which I'd like to be 3, but A is just how much it goes above that horizontal asymptote. So, I don't know, it looks like it's kind of heading toward about 3. So I think that's probably about 0.45, because now when I add the A and the D here, I get 3. Okay, so that's what I want. But I probably want this to be somewhere between 0.4 and 0.5. I can always change those if I need to, but probably something in there. And so it's pretty good. It's just I can't tell, because this B is too much. Now I know I need it to be negative. So, I come down here to the negative, and now what's happening is, it's coming down so fast, it looks like it is a right angle here. That's amazing. Well, so that tells me minus 0.9 is way too big. Now, I'm going to have trouble messing with the slider this way, so I'm going to put this at minus 1 and 0. And so now, I can start sliding this back towards 0 to see if I can get that kink out of it. It's still, oh, finally it's starting to move at minus 0.01. Oh, well, so I'm going to make this minus 0.01 and keep sliding it. It's not really getting too close. Here I'm almost at 0.001. So I'm going to add yet another 0 to this thing, just to make it easier to do the slider. And I still have a ways to go to kind of make it look like that. Now it is finally really starting to look like this there. See, I can see it going through the 3, and I can see it leveling off here at 2.55, which actually, for this curve, if I want it to fit a little better, I think it needs to go up just a little bit. So, I'll start taking it up. That looks a little better. I feel like the bend's not quite right, so I'll play with that a little bit, maybe down there. Well, I think to get this to look a little better, I maybe need to increase this A just a little bit. Again, I'm just kind of eyeballing it. I'm going to take it up to as high as maybe 0.5 almost, or there's 0.485. Now, I need to get the bend a little better, so I bring it back this way to get more of that bend. I don't know. I can bring this up just a little bit more yet. That's starting to look better, but now I'm kind of second guessing, bringing this up and making that bend more. So I'm going to bring this back down. And, maybe even down here as low as 0.42, and then have it not bend quite as much. And maybe even go back down here a little bit more. So that's starting to look pretty good. Okay, but absolutely the data are a little noisy, and so they're bouncing around. But once again, the key aspect here, at least in one sense of the modeling, is after a big rain event on a river, how does the water level drop? I would say you're pretty safe in saying it's an exponential decay, right? It's e to the x with a negative multiplier on the exponent. Okay, and I would say we're pretty safe going with an exponential decay. Right, and that's what the model tells us is, oh, okay, so the water is going to drop in an exponential fashion. So similarly, what we could have done instead was something more like our population model that we are working on the project. And a very timely thing is COVID-19, and we could probably show with that an exponential growth rate of infections, like within the U.S. or something like that, and for at least short periods of time. Typically, if you go long enough, you don't continue with the exponential. But in the very beginning of infectious diseases, they typically follow not an exponential decay like this, but an exponential growth. And so we could have used that data to check if that's true. I'm reasonably sure it is in that case true. So partly because I've looked at it a little bit, but here we're just looking at something else. Water is dropping in a river after a big rain, and what we see is there appears to be an exponential decay at work. And so once again, if you're a geologist or an environmentalist or something like that, and you want to ask, or a structural engineer looking at building dams and that sort of thing, and you just want to ask, well, okay, what can we expect, after rain events as we're trying to design how much water a dam should hold, or various things like that, or how much water we should release from the dam, given that the downstream side of the dam also, it acts just like this as well, a river, and it will have, after a rain event, even if the dam doesn't release more, it gets more tributaries from its tributaries and all that. So, I would feel very comfortable, at least from this data set. Now, I'd want to look at a lot more, but from this data set, I would feel very comfortable saying that we can model these rain events within the height of the river, and the height goes with volume, and so we could have checked volume instead. But I would feel quite comfortable at this point saying, oh yeah, use this decaying exponential model to tell us how the water should leave the river, right? How that height will go down over time. And so there we have fitting an exponential model to some data. And so we've had 3 instances of fitting some data. Again, in every case, we're just trying to do this A, B, C, and D thing. In our couple in the case of the sine function, we needed all 4, A, B, C, and D. In the case of the quadratic, we did not need the B, I guess it was. We just used A, C, and D because B was redundant to A. And in the case of the exponential, the C was redundant to A, so we just used A, B, and D. And so knowing a little bit about how our, our properties of our various functions work, that can help us not kind of do and undo something by, oh, okay, so I decide I need to start changing C, right? And that can't even see that how it changes it here. C would, because this is going clear out to 10,000, I'd have to really change this a lot to see it on the graph. 0.1, close enough. But we would have been spending time changing C, and we just didn't need to. Okay, so there we fit an exponential.